When you saw it, what was the extent of your reaction? Part 1 is an episode of the Degrees of Freedom project videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. This video and the two that follow, when you saw it, what was the extent of your reaction? Parts 1, 2, and 3 address chemical reactors as modeled with extent of reaction and fractional conversion. Moles are not conserved in chemical reactions. A chemical reaction is normally written as a group of reactants go to a group of products. In more specific terms, for reactants A and B and products P and S, we have the stoichiometric coefficient of species A times species A plus the stoichiometric coefficient of species B times species B goes to the stoichiometric coefficient of species P times species P plus the stoichiometric coefficient of species S times species S. Stoichiometric coefficients are probably things you've seen before. Nu sub I is a stoichiometric coefficient for species I. Nu sub I is considered positive for products and negative for reactants. Stoichiometric coefficients are dimensionless numbers and never have dots on them. The chemical species have dimensions of molecules or moles. The chemical reaction C2H6 plus 7/2 O2 goes to 2 CO2 plus 3 H2O can be understood as 1 mole of ethane plus 7/2 moles of oxygen react to form 2 moles of carbon dioxide and 3 moles of water. Because ethane is a reactant with an implied 1 in front of it, the stoichiometric coefficient of ethane is -1. The stoichiometric coefficient of oxygen is -7/2. The stoichiometric coefficient of carbon dioxide is 2, and the stoichiometric coefficient of water is 3. Someone may have told you at some point that stoichiometric coefficients have to be integers. That is not true. They can be fractions. They just are scalings of the ratios of the various species. However, it is rare to see a fraction other than 1/2 or some other improper fraction with a 2 in the denominator, such as 5/2. Other stoichiometric coefficient definitions are possible and are used in different texts, but this definition makes equations very simple to write and to implement on a spreadsheet or in other software. For example, the equation for a chemical reaction can be written as the sum of the stoichiometric coefficients times the chemical species equals 0. There are additional formulas we'll use when writing the first law for chemical reactions that are made simpler with this definition of stoichiometric coefficients. Differential balances were presented in the Keep Your Balance video. We'll use them most often with open steady-state systems. If n dot sub I is the rate of generation or production of species A sub I, for example, moles of species A generated per second, then n dot sub A over nu sub A equals n dot sub B over nu sub B equals n dot sub P over nu sub P equals n dot sub S over nu sub S equals n dot sub I over nu sub I equals psi dot, which is the extent of reaction. Psi dot is a rate in units such as moles per second. By the way, almost all English speakers mispronounce nu. In modern Greek, the letters that we pronounce as mu and nu are actually pronounced as mi and ni. So no, it's not that, it's ni. See the website for the link to the video. Note that for a reactant, the rate of production is negative and the stoichiometric coefficient is negative, so the ratio is positive. The extent of reaction does not depend on the reactant chosen. Integral balances were presented in the Keep Your Balance video. We'll use them most often with closed or batch systems. If n sub I is the amount of species A sub I generated or produced, then n sub A over nu or ni sub A equals n sub B over nu sub B equals n sub P over nu sub P equals n sub S over nu sub S equals n sub I over nu sub I equals psi, the extent of reaction. In this case, psi is the extent of reaction but with no dot. It is an amount in units such as moles. Note again that for a reactant, the generation is negative and the stoichiometric coefficient is negative, so the ratio is positive. Again, the extent of reaction does not depend on the reactant chosen. Here is a mole balance for a reactor with a single reaction. The differential balance is for an open steady-state reactor, and the integral balance is for a closed batch reactor. These are the promised forms of the equations that you should use for a reactor involving one reaction. For the steady-state reactor, the flow rate of species I out is the flow rate in plus the generation, calculated as the stoichiometric coefficient for species I times the extent of reaction. The total molar flow rate out equals the total molar flow rate in times the mole generation rate, calculated as the overall stoichiometric coefficient times the extent of reaction. As you may assume, the total molar flow rate is the sum of the molar flow rates for the individual species. It is true for both the input and output streams. The overall stoichiometric coefficient is the sum of the stoichiometric coefficients for each species. It may come out to be 0. For the integral balance, the same equations hold, only with the molar flow rates replaced with the number of moles. Again, the stoichiometric coefficients are important in the mole balance calculations. Remember that the stoichiometric coefficient is positive for products, negative for reactants, and 0 for inert species that don't participate in the reaction. This is a chemical reaction for burning carbon in air. We have simplified the oxygen-nitrogen ratio in air to be 80:20 instead of the actual 79:21. Nitrogen does not appreciably participate in the reaction. Again, for the reactants, the stoichiometric coefficients are negative, so the stoichiometric coefficient for oxygen is -2, and for carbon it's also -2. For products, the stoichiometric coefficients are positive, so the coefficient for carbon dioxide is +2. The stoichiometric coefficient for the inert nitrogen is -8 on the reactant side and +8 on the product side, which sums to 0, as it should for an inert. The overall stoichiometric coefficient is the sum of the individual coefficients, which equals -2. So at the end, there are 2 fewer moles than at the beginning. In industrial settings, the concern is usually not so much for the extent of reaction, but for the fractional conversion of the reactants. Reactants cost money, and products make money, so a company wants to know what fraction of an expensive reactant is used to make products. The normal desire is for all of it to be consumed, or the fractional conversion to be 1 or 100%. The rate of consumption, or the amount consumed, is the difference between the input and the output. Dividing the difference by the input rate, or the input amount, gives the fraction consumed or converted, hence the fractional conversion. One can calculate the fractional conversion from the extent of reaction, or calculate the extent of reaction from the fractional conversion with the input flow rate and the stoichiometric coefficient. For a reactant, the fractional conversion ranges from 0 for none of it reacted to 1 for all of it reacted. Fractional conversion is not used for products because it ranges from -infinity to +1, and so it doesn't provide useful information. When reactants are combined in stoichiometric ratios, or the ratios of their stoichiometric coefficients, they are referred to as being stoichiometric. If they are not in stoichiometric ratios, and we reacted them until one of the reactants ran out, the one that ran out would be the limiting reactant or reagent, and all of the other reactants or reagents will be excess reactants or reagents. The limiting reactant is calculated in the following manner. The extent of reaction for each reactant is calculated as the amount of or flow rate divided by the negative of its stoichiometric coefficient. The reactant yielding the smallest value of the extent for complete reaction is the limiting reactant, and all of the others are in excess. It is common practice to refer to the fractional axis or percent axis. It is calculated by determining the stoichiometric amount or flow corresponding to the limiting reactant. The stoichiometric amount is then subtracted from the feed amount or flow, and then the difference is divided by the stoichiometric amount or flow. The result is the fractional axis. Multiplying by 100% gives the percent axis. It is important to note that these numbers are defined by these calculations regardless of whether the limiting reagent is fully consumed or not. Let's see an example to demonstrate these calculations. An ammonia reactor reacts nitrogen with hydrogen over a catalyst to produce ammonia. Because of the thermodynamics, the reaction almost never goes to completion. Let's assume that 100 moles per second of nitrogen and 200 moles per second of hydrogen are fed to an ammonia reactor. First, let's determine which species is the limiting reactant and then what percentage access we have of the other reactant. We divide each feed flow rate by the negative of the corresponding stoichiometric coefficient to get the extent of reaction. Because they're reactants, the coefficients are negative, and the negative of a negative is a positive. For hydrogen, the result is 200 and for nitrogen, it's 100. 200 is smaller than 100, so hydrogen is the limiting reactant. We multiply the extent of reaction from the hydrogen by the negative of the stoichiometric coefficient for the nitrogen, getting 200 for the stoichiometric amount. Then the fraction of excess nitrogen is the feed of 100 minus the stoichiometric amount of 200. We divide the result by the stoichiometric amount, getting 1/2 or 50% excess nitrogen. The takeaways from this video are: 1. Stoichiometric coefficient for reactants are negative and for products are positive. 2. The mole balance for a given species in a reactor is that the output is the input plus the stoichiometric coefficient for that species times the extent of reaction. 3. Fractional conversion is for reactants only and is a fraction of the reactant converted to products in the reactor. 4. The limiting reactant is the one that will be totally consumed first if the reaction went to completion. All other reactants are excess reactants. Thanks for watching. This video was brought to you by the DOFPro team.